The first integration technique we're going to look at is substitution. And there's going to be two videos on substitution. So before we get started, what I expect you to know at this stage is some basic integrals. I've listed half of them here, the next page has some more, so just pause here and check that you're sure that you know these basic integrals. So the next page has some more. So it's the integral of a constant, x to the power n, exponential functions, and the trig functions. I'm expecting you to know that. All right, so these are all basic integrations that I need you to know before we can get started with substitution. So let's take a look at some derivatives. Before we look at integration and substitution, let's see why we need it. The first function I've got here is 5x squared plus 2 cubed. To differentiate that, we will need the chain rule, and we know that is 3 times 5x squared plus 2, everything squared, times the derivative of 5x squared plus 2. So that's times 10x. I'm not going to simplify that, because what I want to explain, we're going to use it as it is. Let's look at the next one. Sine of a function. The derivative of sine of a function is cos of that function times the derivative of the function. What's the derivative of 4x squared plus 5x? That is 8x plus 5. All right, and the third one, I've got the root of a function. The derivative of the root of a function is 1 over 2 times the root of that function times the derivative of the function, 16x plus 3. Remember to put it in brackets. You could have, of course, looked at that as to a power of half and wrote the derivative as a half. 8x squared plus 3x to the power minus a half times 16x plus 3. So in all three of these examples, we use the chain rule for differentiation. Now, what substitution and integration does, it sort of undoes the chain rule. It takes the chain rule apart. So if I look at this first example, if I want to integrate this, I want to get back to where I've gotten here. So the integral of this must get me there. So what do we want to look out for? What are some obvious things that we notice? If I see here, I've got a function and its derivative is there. There's some other stuff there, but there's a function and its derivative are both present. We must think of chain rule. Here I've got cos of a function and that function's derivative. We think chain rule again. Same here. So that's one of the things we look out for, is a function and its derivative being present. All right. So this is very similar. This is exactly what we just had. But now let's see formally. We want the integral of this function. Now we can already see this is not a straightforward substitution, straightforward integration, because I've got the product of two things. I've got a function times cos of a function. So I can't just jump out and spit out the answer. There's a bit of work that needs to be done. But what I want you to recognize is I've got cos of something, but that thing's derivative is also there. So what I'm going to do is what's called substitution. Rather than looking at this whole thing, 4x squared plus 5x, I'm going to say, let my u, it's often called u-substitution as well, we like using u for this thing, let u be equal to 4x squared plus 5x. All right, so that's what I let u be equal to. Then the differential du is then going to be equal to 8x, sorry, that's plus 5x, 8x plus 5 dx, differential dx. So what I want you to notice is in this integral, I've got a 8x plus 5 dx present. So when I do my substitution, I'm changing everything to u's, including that. So that's the integral of this whole thing is just du. All right? So I've got cos of u du. Now this looks much nicer. To find the antiderivative of cos of u, we know that's just sine of u plus the integration constant c. All right, but now my question wasn't in terms of u, it was in terms of x's. So I just replace it back, so that's sine of 4x squared plus 5x plus c. Now you can test your answer. How do we test the answer? You take the derivative, sine of a function, the derivative of that is cos of that function, times the derivative of the function, which is what we had in our question. So that's how we use substitution in integration. So let's look at the following one. 4x squared minus 2x is under my root, and I've got 4x minus 1 divided by that thing. So then we say, all right, do I have a function and its derivative present? Now the ugliest part there, the ugliest function, let's look at 4x squared plus 2x. The derivative of that is 8x plus 2. Do I have a 8x plus 2? Not really. But I've got something that looks very close to 8x plus 2. So let's see what we're going to do with that. So let u be equal to 4x squared minus 2x. By the way, our first choice for u doesn't always work. When things get messier, then you know you're probably on the wrong track. For example, let me just fill in here. If you looked at that whole thing and you go, oh, I want to let u be equal to that root of 4x squared minus 2x, then du is going to be 1 over 2 root 4x squared minus 2x times 8x minus 2 dx. Do I have anything that looks like that over here? Definitely not. So that wouldn't work. So we can try something else. So don't be afraid to make a mistake. Try something. If it doesn't work, try something else. So if u is 4x squared minus 2x, then du is 8x minus 2 dx, because we're looking at the differential du. Do I have a 8x minus 2 dx? No, but I've got something very close. I've got a 4x minus 1, but that's just 2 times 4x minus 1 dx. And I need my space back, so let me take this away. What do I have here on the left-hand side? I've got a 4x minus 1 dx. So what would 4x minus 1 dx be? That will just be a half du. Now I can make my substitution. That is equal to the integral of, this whole part is a half du. So it's a half du over the root of u. There we go. Now what I want you to notice is once I substitute, I'm changing my variable from x to u. So there can't be any x's floating around. If you have an integral and there's x's and u's all mixed up, there's something wrong going on there. We want to eliminate all the u's, all the x's, and replace them by u's. Right, so let me just write this. I can take the constant out. We know that. That's the integral of u to the power minus a half du. So that is a half times, add 1 to the exponent, so that's a half, so it's 2 u to the power a half plus c. So that gives me 2 times a half is 1, so it's u to the power a half, so I get 4x squared minus 2x to the power a half. So you can write it as the root as well if you want. And how do I test my answer? I take the derivative and I see I get back to where I started. So that's how we do substitution in integration. All right, let's look at this one. Sine to the power 5x cos x. I like it because I know the derivative of sine is cos, the derivative of cos is minus sine. They're closely linked. Now, as it stands there, I can't just do a straightforward integration. I need to get rid of some stuff. So we're going to use substitution. So I like it. I say let u be equal to sine x because I know the derivative of sine x is cos x dx. Do I have cos x? Yes, I've got cos x there. Fantastic. That worked. That's exactly what I have there, cos x dx. So that is the integral of u to the power 5 du. How simple was that? One substitution and all of a sudden the whole integral becomes very straightforward. So that's 1 over 6 u to the power 6 plus c. If we take it back to x, it's 1 over 6. U was sine x, so it's sine x to the power 6 or sine to the power 6x plus c. Can I test my answer? Yes. Differentiate and you should get back to the answer. All right, so these were 3 examples where we had to do a very little bit of thinking, but most substitutions, the more you do, the more quickly you'll notice. The next 2 are pretty straightforward ones. You can actually do them, if you do a lot of integration, you can do them without a substitution, just by inspection. But I'm going to use a substitution just to show you how we use it. So in this first one, I've got x plus 6 to the power 8. Now, I know how to find the antiderivative of x to the power 8, but not really x plus 6. There's something in there. But now x plus 6, if I wanted to look better, I want to substitute. I want to let u be equal to x plus 6. Now, the derivative of x plus 6 is just 1. So du is just going to be dx. So there's not much of a substitution. That's the same as the integral of u to the power 8 du, which is 1 over 9 u to the power 9 plus c. So take it back to x, that's 1 over 9 x plus 6 to the power 9 plus c. So if you take a look at it, you could have probably done it by inspection, but I'm just showing you how to use the substitution. Same with the next one, sine of 5x minus 4. Now 5x minus 4 is the ugly thing in there, but the derivative of that is just 5. It's a constant. Let's see what we can do with that. So let u be equal to 5x minus 4. Du is then 5 dx. Do I have a 5 dx? No, I just have a dx there. But that's okay. That's 1 over 5 du. So dx I replace by 1 over 5 du. So that is, now that 1 over 5 I can bring straight to the front. That's 1 over 5, the integral of sine u du. And the antiderivative of sine, is it cos or minus cos? Remember to check the signs. The derivative of cos is minus sine, so the derivative of minus cos is sine. So it's minus 1 over 5 cos of u plus c. Always take it back to the variable we started with. So that's minus 1 over 5 cos of 5x minus 4 plus c. So that's what we're going to look at, like these last two. You can do by inspection, but I'm showing you that you're actually making a substitution, but it's very straightforward and simple. In our next video, we're going to look at some more examples on substitution in integration.